dynamic programming. Okay, so hope you are familiar with knapsack problem. Knapsack problem, you have n items and you have weight for that and you have value for it. Okay, so our concern, the problem is going to be, we have to fill in the maximum profit with the capacity as 5. The maximum is 5. Within that space, we have to fill in items which are available here, which will give us the maximum value. So that is all about knapsack problem. So now we have seen different methods how a knapsack problem can be solved. And today we are going to look into dynamic programming method, where how this knapsack problem can be initialized and how it can go about by solving. Okay, so now dynamic programming, as you all know that for every instance of some problem or subset, the solution is being obtained and the optimal solution is kept in store. So now how this optimal solution for each subset which is being stored in using this dynamic programming is going to be related with the knapsack instances, we will just look into this video. So here we know dynamic programming, we have a big problem, and for this big problem we have many small divisions as such. So here what happens, this is going to be a sub-problem or subset and everything, and we have an optimal solution obtained for each and every subset here. So now here also we are going to take for instance wise like how it is going to be solved. So in this knapsack problem, what could be the smallest subset? By adding weight. Weight is going to be initially having 0 weight, or the next one with 1 weight, 2 weight, 3, 4, and maximum, since it is 5, it is going to be maximum of 5 as the capacity. So this is going to be the weight. So here what are they? These are the items. Items in the sense, it is going to be without any item, with first item, with second item, third item, fourth item. So till n number of items which are available, we are going to do it. So for each instance, we are going to get the solution. So if it is going to be an optimal solution, we will keep it as a benchmark, or we can use it for the further iteration. So this is going to be done recursively. So one after the other, we are going to do the iteration and get the solution. Okay, so hope you have understood. We have weight and we have the number of items which are here, maximum number. So for each instance, we are going to find out which is going to be the most optimal subset, so that we can just go about by using that for future use also. So we have 2 instances here for getting the optimal subset. One is going to be, if it is going to be in some state which is going to be i-1 and it is going to be with capacity j, then we will have the optimal solution with respect to that particular place. Okay, so now what does that mean? So here we have the items which are being listed and we have the weights which are being indicated here. So with respect to this, in this table, we have the optimal solution for that particular iteration or the subset. Okay, by chance, if we want to find out a solution for this ith element, okay, so now we have an opinion, or like we can have it as, for this ith element, what is the solution with respect to the j? That is, for ith element, say it is going to be 2 or 3 or anything, what is going to be the value, or whether the capacity is well within the 5, or whether like what is the value, like that. For that particular instance, what has to be taken, we take it. That is normal, like one-to-one mapping sort of thing. But here, we are going to find out the best. So how are we going to find out the best? Previously, if you have a very good solution, that is some value which is giving a very optimal solution, which can be combined as a smaller subset, we go combine and we get the solution. Okay, so we will just work on it, and then when I tell you again, it will be easier for you to understand. So here these are the conditions. We find out the maximum in the sense whether for that instance is the value maximum or is it going to be a combination of previously got subset solutions, so that here the previous value and the combination of it, if it is going to be j minus IW, which is greater than 0. So obviously more than that 0 value, this has to be present. Otherwise, we go to this particular instance, whatever value it is, if it is going to be more, and we just find out if it is going to be less than 0 or we don't have an optimal solution at all. Okay, initially what we have is, if it is going to be, I is going to be 0 and you have some value capacity j, then it is going to be 0 value. And the next initial condition is, you have some value for I, but j, the capacity is 0, it is also going to be 0. Okay, so these are the two initial conditions. That is, I is 0, then j, you have some value, it is going to be equal to 0. In the same way, if I value is there and j is going to be 0, it is going to be 0. Just I have marked here, isn't it, as general condition. So here also we can go about by taking by the initial condition. I is equal to 0 and j we have as j1 is going to be 0, j2 is going to be 1, j3 is going to be 2, j4 is going to be 3, j5 is going to be 4 and j6 is going to be 5. But here, since I1 is going to be 0, we take this one, the entire row, as 0. Okay, we just have it as I0 for our convenience. Okay, so now how do we go about? Now we will just look into this condition. J1 is 0, okay, and I0 is also 0, but we have found out. But now here we just say, if I has a value and j is 0, then there also the value is going to be 0. So here out here, it's going to be 0, 0, 0. So I2, I3, I4, we have all the values 0. The meaning is, you don't have any item, so you don't have any capacity there filled. You don't have any weight which has been assigned for any item. That is what it means. Okay, so now we will just go one step after the other. So now what is this I1? Is nothing but this item 1. So item 1, it has a weight of 2 and the value is going to be 12. So W1 is 2 and value is going to be 12. This item number 2 is going to be of weight 1 and value is going to be 10. When it is going to be item number 3, this weight is going to be 3 and value of it is going to be 20. So here similarly, item number 4, weight is 2 and value of it is going to be 15. So now we will just see how we can fill in all these. So now the weight of this particular item number 1 is going to be 2. So obviously it will not fit into the first box. It is of weight 1. So if it is weight 1 and now we have a capacity of 2, what can we fill with? It is obviously we cannot fill it. So it is going to be 0. So now we have only item number 1 and the weight is going to be 2 and now we have this one here. And what value can we have? It is maximum 12 we can have here. Okay. So now we don't have any either item here in this first initial step. We just have only item number 1 available. So all these places we can just fill it up with 12. That is, maximum capacity is going to be only 2. So beyond this we cannot add anything. We don't have any item at all. So it is going to be 12 throughout. So now the second item has come into. It is recursively adding one item after the other. So at this point, what happens? So now what happens here is, it is value, that is the weight is going to be 1. So this weight is going to be 1 means it can be put here. The value is going to be 10. Okay. So now we have 10 as the value which is being given. So when it comes weight as 2, it is now a conflicting factor that now already item number 1 is there with this 12, and now you have item number 2 which is there as 10. Okay, the weight for this is 2 and here it is 1. Okay, so which is maximum, 12 or 10? So obviously we know the maximum as 12. So now choosing which is the optimal solution, we will have the answer as 12 here. Okay, so now that is what, choosing which one is best here. Okay, then now after this, when we go to this level, it is weight is going to be 3, which can be 1 plus 2 or something like that. So I can add both item number 2 and item number 1 so that I will be able to get a more optimal solution. So now 10 plus 12, I will be having it as 22. I have added both the items there. So now I don't have anything else. So this row is being completed. Hope you have understood till here. So what happens next is, I have the next one, item number 3, which has to be added. Now I have this value which is going to be 3, and here 3 means it is not going to fit. So this 10 will be the most optimal solution. So here the capacity is going to be 3, and here we have found out that 12 is the most suitable solution. Now here we find that 22 we have already got, and this value for I3 with the capacity of 3 is going to be 20. So now 20 or 22. So now 22 is more than 20. So we have that itself. And now here it is going to be with capacity 4. How do we have? It can be 1 plus 3 we can just add, and we can see whether it is going to be okay or not. Or that is, first item is going to be 10 and the third item value is going to be 20. So obviously the value is going to be 30. Okay, so now the earlier step we had it as 22. So now is 22 big or 30 big? So now our concern is 30 is bigger. So we have this one as the solution. So for 5, this is with respect to this one we have found out. And with 5 as the capacity, we can have item 2 and 3 together to give us 5. That is 12 plus 22. That could be 34. So now the comparison is 22 or 34. Which is bigger? 34 is the bigger number. Okay. So now at the end of the fourth iteration, that is 0 we have done, first, second and the third one. Now we have found out this is the most optimal solution. Okay. So now if these weights are being added, that is weights with a combination of 2 and 3. If we, okay. Sorry. 2 and 3, we get a solution as 32. And now here, when we just see first item, only one item can be added, and now this capacity is 2. So it is now decision. Now as we have seen, now here we have this weight as 2. Okay, so 2, we have 2 options. that is weight 1 is also there, and weight 4 is also 2. So the value for weight 1 is going to be 12, and for value for the item 4 is going to be 15. So now it is our concern to choose which is maximum, whether it is 12 or 15. So which one can we choose? We can obviously have this as our optimal solution. Okay, so now so far we have just had it as for this 3 as the capacity. It was item number 1 plus item number 2, that was with value 10 and 12 we just went about with, and we have this. And now we have just found out that this 12 can be replaced by 15. So 10 plus 15, it is going to be 25, which is going to be the most optimal solution. So it is going to be a combination of item 2 plus item 4 together, which is going to be 1 plus 2. The value is going to be 3. The value for this one, the cost was 3. The cost is going to be 10 plus 15, that is 25. Okay. So now for the fourth one, when it has to be 4, we just saw that it can be a combination of 1 plus 3, that is the second item and the third item. So the value is obviously 10 plus 20, that is 30. We don't have any other choice, I guess. Okay. So now it is for the last item which we have to look into. So now which is the last item with capacity 5? Earlier we had the values as this plus this, that is item number 1 plus item number 3. So item number 1 was with value 12, and item number 3 we have value as 20, and the answer was 32. So now we have this same value, or that is we can have it as item number 4 plus item number 3 here. So item number 4 value is going to be 15, and now we can have the 3 1 as 20, so 37. Okay. So now 35. 35 would be the most reasonable. Now we have to find out whether there is any other possibility or any other combination which are possible. So 2 plus 3 we have, and we can also have another combination, that is 2 plus 1 plus 2. Okay, so that is we can have as item number 1 plus item number 2 plus item number 4. Okay, it is going to be capacity of 2 plus 1 plus 2. So that is also going to give me 5. Okay, so we'll just add up the weight and see what could be the cost. So I have 10 for the item 2, and for this one item number, I'm so sorry, item number 4 is going to be 15. So now if I add 12 plus 10 plus 15, it is going to be 37. So now I have 3 different combinations, that is one here, another here, another here, for the capacity as 5. Okay, so now which one is most optimal here? I have 32, 35 and 37. So which is the maximum value? It is obviously going to be 37. So now I take it as the optimal solution. So this is how I construct this dynamic programming used knapsack problem, the table, that is for each instance I keep my best solution, that is the optimal solution. Hope you have understood how we calculated. We had two initial conditions here, that is if it is going to be 0, j, it is going to be 0, I, 0, it is going to be 0. After that, we were to find out which is the maximum, whether it is that state what we have got is the maximum, or the previous value which we have already attained plus what is to be attained, is it going to be the maximum. So ultimately this is the goal, or this is the solution. So for my 5 capacity, okay, adding the weights, that is 1, 2 and 4, I get a solution as 37. When we just look into this box, that value is going to be the maximum. Okay, so that is the optimal solution. So these are the two conditions how we go about by getting the optimal subset with respect to that particular area. What is the capacity or the cost which we have, we can just take it, or it is going to be somewhere, some weight more than 0 but less than the maximum capacity. If we have already calculated the sum and we have kept it in store, we can make use of it. Okay, so if that is the condition, then the previous value plus whatever is going to be computed, we can just use and we can make a use of it in our tableau for computing. So this last value with the all items having a combination of those and with the maximum capacity, what value we have got will be our goal or the answer. Okay, hope you have understood this dynamic programming method, like how we solve this knapsack problem and how we arrive at this particular point. So now we are just dealing with analysis of algorithm. So n items and w weight we have. So for each and everything, it is going to be a recursive way of finding out the solution. So the time complexity and the space complexity with respect to this knapsack problem dynamic programming with respect to the number of items and the number of weight. So for each weight 0, 1, 2, 3, 4, 5 we have, and for number of items 1, 2, 3, 4 we have. So 4 into 5, that is n into w is going to be the time complexity. So it is going to be theta. Okay, so this is the time complexity, and maximum space occupied also will be n into w. Okay, so hope you have understood. We already know about knapsack problem. Now with respect to dynamic programming, we have seen how to solve the problem. Okay, hope you enjoyed the video. If you have not subscribed, please don't forget to subscribe our channel, and if you like it, please click on the like button, and any comments, please do mention. Thank you. Have a great day.